The new pictures gained by the James Webb Space Telescope have left scientists surprised, uncovering an unanticipated reality about the universe. Instead of basically widening our view of the universe, these pictures have uncovered a perplexing truth. Our current understanding is lacking to grasp the huge conceivable outcomes of the universe in its beginning phases. The current speculations concerning the origin of the universe are starting to approach their limitations, inciting the need to revisit and explore alternative theories concerning its development. This present circumstance leads to the critical inquiry of how the universe was created and why these discoveries are bewildering even to the most prepared specialists in space studies. Thus, there's a pressing need to probe further into the genuine nature of the Big Bang and the continuously shifting details it presents. It might now be necessary to reevaluate the Big Bang hypothesis itself, as it has often been misunderstood in popular discourse. The Big Bang was not merely an explosion within a pre-existing space, but perhaps it marked the beginning of space itself, occurring roughly 13.8 billion years ago alongside the emergence of matter and time. A fundamental concept in true science and cosmology is the idea of a singularity, a point where gravitational forces become so intense that space's curvature becomes infinite. Following billions of years since the universe's formation, we now observe that our cosmic dwelling place exists as part of an expansive and interconnected structure. For researchers, this represents a fundamental aspect of the universe's stability, emphasizing its continuous evolution. The universe does not simply expand into pre-existing space. Rather, space itself continues to grow. According to standard theories, the first stars are believed to have started emitting light approximately 200 to 300 million years after the Big Bang, marking the end of the so-called Dark Age of the universe. This was the period when the first luminous celestial bodies began to coalesce, eventually forming mature galaxies. However, the rate at which these galaxies developed remains an unresolved mystery. A critical breakthrough occurred on July 22nd, when the James Webb Space Telescope released its first set of images, revealing several galaxies, some of which already existed around 300 million years after the birth of the universe. Although these galaxies were far younger than those observed today, they were noticeably smaller and less massive, consistent with scientific models of that time. In the universe's early stages, the matter density was too low to form galaxies as massive as the ones we see today. The discovery began with 6 unexpectedly redshifted bright spots detected by the James Webb Telescope, triggering one of the most significant astronomical puzzles of recent times. These newly discovered galaxies, despite being comparable in age to previously recorded ones, appeared nearly as large as our Milky Way. This revelation has ignited intense interest within the field of Big Bang cosmology. After examining a series of images captured by the telescope's near-infrared camera, researchers confirmed the presence of these distant galaxies using redshift data, determining that their light had traveled for over 1 billion years before reaching Earth. Consequently, these galaxies were already in existence between 570 and 700 million years after the confirmed Big Bang event. This remarkable finding challenges conventional cosmological assumptions, which predicted the formation of much smaller and less developed galaxies during this era of the universe's history. Interestingly, the James Webb Telescope revealed galaxies nearly as massive as the Milky Way, defying previous expectations. The stars bound together by gravity within these galaxies had already accumulated mass exceeding 10 billion times that of the Sun. One such galaxy even showed signs of a mass greater than 10 billion solar masses. However, whether this hypothesis is entirely accurate remains uncertain. Even if this assumption holds, the mass in the early universe would be significantly higher than expected, raising further perplexing questions. This discovery challenges almost all traditional cosmological theories. Even if just one of these galaxies is confirmed, it would compel us to reconsider our previous beliefs about the formation of these early cosmic structures. The matter density in the early universe would have to be much greater than initially estimated. An alternative explanation could be that these galaxies formed in a completely new way that is currently unknown to us. These discoveries are prompting scientists to reconsider the Big Bang theory. Many space experts express frustration over these findings, often voicing their concerns in scientific publications. Those challenging current models are frequently labeled as unconventional or extreme. Nevertheless, it is clear that even the staunchest defenders of the Big Bang Theory are grappling with unresolved questions. These inquiries include fundamental issues, such as how something could have emerged from nothing 13.8 billion years ago. Could something truly arise from nothing? Was there a catalyst for this event, or did it happen randomly? Stephen Hawking famously argued that the concept of time, as we understand it today, began with the Big Bang. This suggests that the process could not have been initiated by any external force or triggered by another event. Similar uncertainties exist regarding the uniformity of radiation and matter across the universe. No matter where we look or at what distance, we observe the same distribution of structures, clouds, and radiation throughout the cosmos. Contemporary researchers explain this phenomenon using the theory of cosmic inflation. Other scientists have expanded on this idea, suggesting that the universe has expanded in a more chaotic manner. According to this perspective, expansion occurred only in specific regions, like bubbles, while other areas continued to evolve indefinitely. This model presents the intriguing possibility that other universes could exist within these expanding bubbles, each governed by its own set of physical laws. This perspective implies that our universe might not be the totality of existence, but rather just a part of a far more complex and vast structure. Within this framework, the idea of an eternal cycle of collapse and rebirth for the universe is introduced. However, this is not the only cosmological perspective. For instance, an article published in NASA's Big Bang magazine in 1955 suggested that the universe may never have had a Big Bang and that it has existed infinitely, possibly for an eternal duration. In this interpretation, the universe's expansion would be non-existent, with matter gradually forming over time, creating the illusion of slow, continuous growth. One of the more fascinating theories emerges from quantum physics and string theory. Some studies suggest that our universe and everything within it could be a projection or simulation originating from a higher dimensional reality. While this may sound like the premise of a science fiction story, it has connections to the Kardashev scale, which measures a civilization's energy consumption based on its ability to harness the power of an entire universe. If a Type 3 civilization existed, capable of utilizing all of a universe's energy, it could have created a perfect simulation of a universe. However, validating this scenario presents significant challenges. The development of these early galaxies raises profound questions about the structure and evolution of the universe. If the standard model of cosmology cannot fully explain these observations, alternative theories must be considered. Some researchers propose that the early universe experienced periods of rapid star formation that far exceeded current predictions, possibly driven by unknown physical mechanisms. Another possibility is that the fundamental laws of physics may have behaved differently in the early universe than they do today. If this is the case, it could require a re-evaluation of our understanding of gravity, dark matter, or even the nature of time itself. Some scientists speculate that exotic forms of matter or energy might have played a crucial role in accelerating the formation of galaxies, enabling them to grow much faster than previously thought. The implications of these discoveries extend beyond cosmology. If galaxies formed more rapidly than expected, it could influence our understanding of black holes, dark energy, and even the fate of the universe. One major challenge in modern astrophysics is explaining how supermassive black holes, millions to billions of times the mass of the Sun, formed so early in cosmic history. The presence of massive galaxies in the early universe suggests that these black holes may have grown at an unprecedented rate, defying current models of accretion and stellar evolution. Additionally, these findings have sparked renewed interest in the concept of a multiverse. Some cosmologists argue that the anomalies observed by the James Webb Space Telescope might be evidence that our universe is just one of many, each with its own set of physical laws and conditions. This idea is supported by certain interpretations of quantum mechanics and string theory, which suggest that multiple universes could exist within a vast, higher dimensional space. If the multiverse hypothesis is correct, it could provide answers to some of the most perplexing questions in physics, including why our universe appears to be so finely tuned for life. The values of fundamental constants, such as the strength of gravity, the charge of the electron, and the expansion rate of the universe, seem to be precisely set to allow for the formation of stars, planets, and biological life. Some scientists argue that this fine-tuning could be explained if an infinite number of universes exist, each with different physical parameters. In this scenario, we happen to live in one that is suitable for life simply because we could not exist in any other. However, the multiverse hypothesis remains highly speculative, as it is difficult to test or observe directly. Critics argue that without empirical evidence, it remains more of a philosophical idea than a scientific theory. Despite this, the discoveries made by the James Webb Space Telescope suggest that we may be on the verge of a paradigm shift in cosmology, one that could challenge our deepest assumptions about the nature of reality. As scientists continue to analyze the data from the James Webb Space Telescope, new questions will undoubtedly arise. Future observations may provide additional insights into the formation of the first galaxies, the properties of dark matter, and the origins of cosmic structure. Advanced simulations and theoretical models will be necessary to interpret these findings and integrate them into a comprehensive framework of the universe's evolution. Ultimately, the significance of these discoveries lies in their potential to reshape our understanding of the cosmos. Whether they confirm existing theories or point toward new physics, they remind us that the universe is far more complex and mysterious than we ever imagined. The journey to uncover its secrets is just beginning, and the next generation of telescopes, experiments, and scientific breakthroughs will continue to push the boundaries of human knowledge. Gigantic systems bring up indispensable issues about the roles of dark matter and dark energy, two secretive substances that make up the greater part of the universe's mass and energy. While dark matter is believed to provide the gravitational structure required for galaxies to form, researchers still lack a clear understanding of its distribution and characteristics in the early universe. Due to these unresolved challenges, theoretical physicists are exploring alternative cosmological models that challenge the standard theory of the Big Bang. Some of these ideas suggest that our universe may be just one of many within a vast multiverse, each governed by its own unique set of physical laws. These ideas, emerging from string theory and quantum cosmology, present an increasingly complex and interconnected universe than previously considered. One such speculation gaining popularity is that of eternal inflation, in which universes are perpetually created within a larger expanding space. This suggests that our universe could be one among an infinite number of others, each with distinct physical properties. However, the challenge lies in obtaining observational evidence to support these theoretical hypotheses, as they push the boundaries of what can be tested through scientific means. Another provocative idea suggests that our universe could exist within a computer-generated simulation, drawing comparisons to advancements in artificial intelligence and computational science, where simulations can replicate intricate systems. If this idea proves true, it would fundamentally change our perception of reality and provoke profound philosophical and scientific questions regarding the nature of existence itself. As observational cosmology advances, instruments like the James Webb Space Telescope, with its unparalleled sensitivity and resolution, promise to unveil even more of the universe's mysteries. Future observations might provide deeper insights into the universe's earliest moments, potentially offering clues about its ultimate fate and the fundamental principles governing its continued evolution. Meanwhile, particle physicists remain dedicated to unraveling the fundamental particles and forces that shape the universe. The quest to unify gravity with the other three fundamental forces, electromagnetism, the strong nuclear force, and the weak nuclear force, remains a central objective in theoretical physics. In the field of quantum mechanics, debates continue about the nature of time itself, with some theories suggesting that time could evolve or even behave differently at the most fundamental levels. Understanding the true nature of time within the context of cosmology could transform our comprehension of the universe's origins and development. Furthermore, The search for extraterrestrial life continues to captivate both public interest and scientific research. The discovery of exoplanets, planets orbiting stars outside our solar system, has expanded our knowledge of planetary diversity and the potential for habitable environments beyond Earth. Future missions, such as the James Webb Space Telescope's analysis of exoplanet atmospheres, could detect biosignatures pointing to life beyond our planet. As scientific exploration advances, philosophical inquiries into humanity's place in the universe intensify. The pursuit of answers regarding existence, the likelihood of intelligent life elsewhere, and humanity's future in space exploration will remain central to discussions across both scientific and philosophical fields. As progress continues, the questions surrounding the origins and nature of the universe become more pressing. Discoveries made by the James Webb Space Telescope have highlighted the need for new approaches in understanding the universe. While traditional models of cosmic evolution have been foundational to cosmology, recent findings challenge these ideas and open the door for new paradigms. These discoveries suggest that our knowledge of the universe's history and structure may need to undergo a fundamental shift, one that embraces the complexity and uncertainty inherent in the cosmos. Cosmologists now face the challenge of revisiting their assumptions about the Big Bang and its aftermath. The idea that the universe began as a singular, explosive event in a state of infinite density is still widely accepted. However, new data raises serious questions about the accuracy and completeness of this model. The discovery of massive galaxies in the early universe suggests that the process of galaxy formation may have been much faster and more efficient than previously thought. This has led to a reassessment of how galaxies form and evolve, with researchers proposing new mechanisms that could explain the rapid development of early cosmic structures. One such hypothesis involves the possibility of dark matter and dark energy playing a more significant role in the formation of galaxies than previously assumed. Dark matter, which is believed to exert a gravitational influence on visible matter, may have played a crucial role in shaping the structure of early galaxies. However, its exact properties remain elusive, and its behavior in the early universe is still poorly understood. Similarly, dark energy, which is responsible for the accelerated expansion of the universe, may have contributed to the rapid evolution of galaxies and other cosmic structures. Another area of inquiry is the role of cosmic inflation in shaping the large-scale structure of the universe. The theory of cosmic inflation suggests that the universe expanded exponentially in the first moments following the Big Bang, leading to the uniformity we observe in the cosmic microwave background radiation. However, recent observations, including those made by the James Webb Space Telescope, have raised questions about the validity of this theory. Some scientists now believe that inflation may not have been a smooth, uniform process and that local fluctuations could have influenced the formation of galaxies and other structures in the early universe. These emerging questions highlight the need for a more nuanced understanding of the universe's origins. While traditional models like the Big Bang Theory have provided a strong foundation for cosmology, new data is forcing scientists to reconsider many of their long-held beliefs. This is no easy task, as the implications of these discoveries challenge some of the most fundamental principles of physics. Nonetheless, the pursuit of answers to these questions is essential for advancing our understanding of the universe. In addition to revisiting established cosmological models, these discoveries are also prompting new avenues of exploration into the fundamental nature of reality. The concept of space-time, which has been a cornerstone of our understanding of gravity and the behavior of matter, is now being scrutinized more critically. Emerging data suggests that space-time itself may be more dynamic and flexible than previously thought. Some theories propose that space-time could be subject to changes that are not yet fully understood. As scientists continue to probe the mysteries of the early universe, they're also looking to other fields of study for insights. Quantum mechanics, which governs the behavior of particles at the smallest scales, may hold the key to understanding the fundamental forces that shaped the universe's formation. The relationship between quantum physics and general relativity, Einstein's theory of gravity, is one of the greatest unresolved problems in modern physics.